Good morning. So the paper we're going to present is on integrating planning and control for UAVs to design path planners. So there are several applications from military to civilian. So they're using everywhere. So one of the most used application is on to try to navigate in the presence of obstacle environments. So that's where the entire path planning comes into picture. So the idea is that we want to design path planners so that it can move from this given source S to a goal G in the presence of obstacles. So there have been plenty of research literature on path planning. So in a broad sense, we can categorize in three categories. One is on search, control, and sampling based. So if you look at search-based path planning, the idea is to discretize the entire search space, and then you have obstacles, and then use the discretized planner to find a path from source to goal. So the good thing is that they are pretty much you have pretty good deterministic paths. So they are pretty interesting. They're good for human operators who are trying to oversee the operations to have some deterministic behavior on the UAV side. And there are plenty of algorithms on top of it. So the only main issue comes, or the main complexity is when we add kinematic constraints for the UAV. So basically we have the XY, and then you have, for the UAV is going to be on the wind, its magnitude and direction. Let's say assume that we have an estimator that gives information, and then I have a control which is going to be my lateral acceleration, on which I need to control the rate at which I make the heading angle change. And another constraint is that my heading angle, the maximum I can give is bounded between certain rate. Right? So if I use this, and if I use the previous planner on which I do a path, then it will end up into an obstacle because it did not take care of the possible turn rate constraints on the vehicle. So other than this constraint, so let's say that we use some kind of a lattice-based planners that have been used earlier. So the main issue is that the number of primitives that you need to design, because you have a continuous space from minus omega to omega, so you don't know like how many how many number of primitives that you really need. And another thing is that even while planning, you don't take care of the environmental disturbance. So it's only after the plan you do it. So on the other side, you have control base, wherein I can design a time optimal path planner with an objective function that I want to minimize only the time. And given the boundary conditions, that is my initial state and that is going to be my final state. So idea is that you solve a Riccati equation, which is going to be computationally intensive because of the nonlinear constraints that are going to associate with this. So there are plenty of nonlinear optimal control solutions, but the main issue is still the computational intensive. It is pretty intensive computationally, and it's mostly on offline. So this can be more or less like a reference path on which you again redo it online. Apart from this, you have sampling-based planners. So the main issue is that although it's pretty computationally cheap, but it's non-deterministic, except like say recently of the RRT star. But even while planning, you don't consider the environmental disturbances explicitly. Yeah. So the objective of what we thought would be interesting is that let's say that we need to find a path, right, with kinematic constraints and disturbances taking online, or basically like while planning itself. So you want to ensure that there are some deterministic properties along while finding the path, and idea is that we want to use search-based planners like say A star, and try to integrate control while doing the search. So the question is like how can we do it is what is going to be part of the next few slides. How to integrate control with the A star. So the main issue with the control actually comes in when you want to find the cost from say CXY to C prime XY. So and this is the heading angle of the vehicle at this cell. So if the cells were pretty large or pretty long enough, then basically like this will go from CXY to C prime XY in an easy way. But if they are short, then the question is like, even if they're short, then the question is like, what is the actual path length that you really need from this? So the thing is, what we do is we'll try to formulate this as a path following problem. So wherein in the path following, you have the kinematic constraints, and I know the position of the vehicle, let's say here, and the two cells are going to be like two waypoints for me. Right? And I know what is the heading angle, which is going to be my psi, and I know what is the line of sight angle, which is basically my theta. So the goal is that in the control thing is that as t tends to infinity, I want to make sure that my cross track error, which is the d, the vehicle position from the path along which I want to go, must tend to 0, and then even my heading angle should be equal to 0. So if only cross track error is 0, then what will happen is that you have your vehicle that can do a sinusoidal motion along the path, which you don't want to have. And if it don't take the heading angle to be 0, then you can have a path which is going to be very parallel to the desired path that you want to go. So the path following problem basically ensures that you track the path as you go. So a simple thing what we do was that we just used a nonlinear guidance for giving the command to the x dot or psi dot. So the idea is that in a nonlinear guidance, you take d and you take something greater than d, which is going to be an L, you say, and then you just draw a circle around this path. So then this circle intersects with this path segment at 2 points, say Q and Q bar, and then take the point which is closer to the next waypoint, which is your C prime XY. And then you find the angle between the velocity vector and the point between is P and Q. So that's going to be your eta, and you just control that. So as you move your vehicle towards the waypoint, towards the path, then basically your eta tends close to 0, and then you're moving along the path with almost close to 0 acceleration. So this is where the path comes into picture. So the issue, main thing is going to be on the heading angle on which you start. So if this is my vehicle, and this is going to be the path between the waypoints given by these two. So that is what is going to be the true cost that I'm going to associate as a g cost into my planner. So that's my actual distance. So there are two things. One is that as far as A star is concerned, this is the direction, or this is the segment that I'm going to use. But associated with this, I also will have the corresponding xy psi of the true planner. That's because your incoming angle into this cell is dependent. That is going to tell me what is going to be my next path cost from this cell to the next cell. Right? So if there are multiple paths that are discovered, then we just take the one that is the best. So the issue is that because of the kinematic constraints, you may not always reach from center of the cell to the center of the cell, but you may reach somewhere close by. But still, we consider that as if it has reached inside the cell region. So next is that it is not always that the path from cell Cx to C prime XY will always be within those two cells. Sometimes, because of the wind disturbances, you can have a trajectory like this, wherein the path actually goes to some of the cells into the next cell. Right? So this is due to disturbances as well as due to subspace discretization. Let's say that if I have a very small discretization, then what will happen is that my turning radius is not good enough to reach from this cell to this cell. Rather, I go visit some few other cells before coming into the cell that I want to meet. So if so the idea is that if I do that, then basically like I'm using some additional information on this part because I'm getting the paths even to other cells, even though my actual goal was not to find those paths. Right? So that's where we use it like the dynamic control A star base, wherein we try to say that even these cells that have been visited by a path will also have some associated trajectories to it, which I can use it as a cost. So this will help me in doing a large space exploration, even with smaller number of entities. So then we did two things to evaluate this. One is on simulations, and the other is on experimental. So in the simulations, we did compare with kinodynamic RRT, so that gives you closer to the kinodynamic part. And then we did another one, which is basically the traditional way of doing greedy star, and then follow it up with checking if it's feasible by connecting those splines. And then the testing conditions were on different environments, different obstacle densities, wind, speed, directions, and the resolution of the grid. So for each case, we did for 100 simulations, and the heuristic cost was Euclidean. So the aircraft speed is 5 meters per second, and the wind is half of it is 0.5 meters per second. And see, these are the results for that. So this SR is basically the success rate, SE is the average simulation cost, and RT is the runtime. So here we can see that CBA star, which is basic control based A star, and DCBA star, they have very high success rate compared to the greedy A star, followed by the spline based validation or the RRT connector. Right. And the cost is also very lower than the other ones. Yeah, so only thing is that your runtime, because if you do both the control and the planning at the same time, the runtime is much more higher than the other two. So what will happen when we increase the obstacle density? So in this case, even as I increase the percentage of number of obstacles in the subspace from 1% to 20%, so you can see that the CBA star and BCA star, they tend to perform consistently with a higher success rate. Right? So even the cost is almost like on the same side, and their runtime is interestingly like it starts to decrease as we increase the percentage of obstacles. It's because if such space is filled with more obstacles, and the amount of such space on which you need to find solutions tends to reduce as you increase your obstacle space. Right? So effect of wind is interesting on the side wherein you don't have any kind of an paths for RRT or the A star when its variance is very close to the actual flight of the vehicle. And on the RRT connect, here A star really doesn't work anything more than half the wind speed. And similarly, we have similar kind of costs, and then there is a slight increase in the runtime because you need to search for more, right? So same thing with grid resolution. So if I go for very fine grid, especially when there is a high amount of obstacle space, then only DCBA star is performing well, while the BA star, CBA star is always like it could not do any kind of solutions. So, and interesting, like so in the one way, like BCA star is performs pretty well in terms of finding such good paths and lower cost paths. Yeah. So not only just that, how would the system behave when I have some kind of a random winds, or basically like say wind gusts that, or wind fields that change over time. So in this case, when we have a higher change in field, which is going to be between 0.75 and 1 of your VA speed, then even then like BA star, CBA star, and BCA star pretty good, with almost consistent path lengths and almost very low computational time required. So then after having good interest in this, then we thought, okay, let us try to do some kind of an experiment and then see if it is really varied with a virtual world. So this is the world that we took, so source and destination. So it's like 100 by 100 meters, and so quad rotor speed was 2.5 meters per second. Yeah, and then so basically like the quad rotor, this is a 3D iris, so it operates in two modes. One is given a wave path, so it basically orients towards that, then it basically becomes like an holonomic. And the other mode is on the spline base, which basically it uses the spline kind of an integration between two wavepoints. So that's where we used it in the spline base mode with 5 meters as the turning radius. Yeah. So this was over the campus that we did the experiment on the, I didn't put the wind speed. So wind speed was something around 1 meter per second. It was much less than half, but there was some wind. Okay, so for this was the oil on ridge, and then you have the planned path, which is the straight line. This is the CBA star path, and then you have the simulated version of it, which is this, and you have the experimental, which is in between the simulated and the A star path. So in one way, we said that okay, this is, works well, but then we need to still validate under very high conditions how it works. So in conclusion, we proposed a mechanism to integrate a star with control, and then we experimentally demonstrated it, but then we need to still find efficient ways in which you can minimize the computation time, and then try to get some theoretical properties on, especially on completeness. Next.
Hi, two questions. Two questions.
Yeah.
Yes, that's fine. How do you relate to hybrid A star? And now we have seen that the computation times are quite high at the moment. What about three-dimensional computation? I mean, you're dealing with quadrotors after all, so you can also change altitude.
Yeah, you can change the altitude. We haven't thought of extending to three-dimensional yet, but you can do it. So it depends on your path cost that you want. Whether I think as you increase your altitude, you have cost associated with both the segment as well as the energy associated with that. Right. You may want to go a much lower height rather than a higher, because your energy cost increases when you climb up. But you can put it like a cubish kind, and you can try to do it.
But what's the difference with your algorithm with a hybrid A star?
So basically like that.
Can I answer that? So, yeah, sure. Also, so the sorry, I can talk as well. No problem.
Yeah, how do
So the way we sort of do this is like the way hybrid is the explore. It uses a controller in between, kind of a simulated planner.
Well,
okay.
Otherwise, we make up like.
Yeah.
So the basic difference from hybrid A star in this is that we start within a grid. We always try to use these waypoints to connect sets. But what hybrid A doesn't do is that while we connecting cells in the grid, we try to explore what other cells we are growing. So hybrid A star, even if it's going for a local planner, it uses a static graph underneath. So in our case, we build the graph kind of online while we are discovering paths. So the strategy of exploration is still grid-based, grid-connected, but as we have wind and other dynamic things, while trying to connect to grid waypoints, whatever we find as knowledge, we integrate that in research. But it's very close.
Thanks. To both of you.
Other questions? I have one question about the computation time and the actual deployment on a real architecture. So, in simulation, you had some trend about computation that was not so good with respect to also the other approach. Which is the more crucial, in your opinion, which is the more crucial parameter or aspect that is, let's say, the first point to address for reducing the computation time in your approach?
So the main thing is it's the control part when I compute the G cost from cell to cell. That's where I need to think of reducing the cost, the main computation time. So if I reduce that, then basically like it comes to A star kind of. So that's an additional add-on top of it.
Do you have plan for
Yeah.
such improvement?
Yeah.
Any other questions? Let's thank again the speaker. Next talk is another journal track paper. The speaker is Ezra Erdem. The paper is entitled "The Systematic Analysis of Levels of Integration Between High-Level Task Planning and Low-Level Feasibility Checks." This is a joint work with Peter Schuller and Volkan Adaglu.
Thank you.
I'll call you back.
Okay. So. So this work is also about integration of planning, task planning with feasibility checks. So we are interested in bridging the gap between high-level reasoning that is done in discrete domains with low-level feasibility checks that is done in continuous domain. So with a task plan, we understand a sequence of actions as we do in AI planning. And with feasibility checks, we understand like reachability checks, collision checks, balance check, force closure, graspability, temporal feasibility that are done, using continuous mathematics. So let me explain it further with a kind of video. So here we will see a robot, and the task of the robot is rearranging objects on a cluttered surface on a table. And here the robot has to decide the order of his own actions, like moving, picking, or placing. But also the robot has to check for feasibility of these actions, like for instance whether it can reach the object, grasp the object, or whether there is any collisions when it places the object. So we want to integrate these two sorts of reasoning in these applications. So this is a topic of very of interest to many researchers in AI and in robotics, and there are many papers. So this just gives you some idea about different research groups who are interested in this topic. And there are also many events in top AI and robotics conferences.
Thank you.
Thank you. So. At AAAI in January there was one event, like last month at ICRA there was another one, and in 2 days at RSS there is another event, and as Iran also advertised there is another event at IRO. So this is an important topic for integration of AI and robotics. And there are various approaches, and some of them are like what we call search-based. So the idea is to modify the existing search algorithms or to introduce new search algorithms for planning where these feasibility checks are integrated into the algorithm. And there are also some approaches where this integration is done at the representation level. And the idea is to use the planners as they are, to use the feasibility checkers as they are, but to do the integration at the representation level. So we are interested in the question of integrating task planning and feasibility checks at the representation level. And for that, to be able to understand the usefulness of such an integration, we had to find a formal framework that allows us to represent this integration. And we decided for ASP answer set programming. It provides an expressive representation language and efficient solvers, and it has been applied in in various applications, and some of them are even applied in industry. And here the idea of ASP is very similar to what we know from SAT. So we represent the task planning problem by a set of formulas, but in a non-monotonic logic formalism. And we compute the models of these formulas that are called answer sets using special solvers that are called ASP solvers. And once we compute the models, then we extract the plans from these models. So this is the idea behind ASP, and we represent the robotic domains in this formalism and also integrate the feasibility checks into these formulas. So the formulas in this representation look like this. So this is very much similar to the rules that we know from Prolog or standard logic programming. But the difference is that, so the atoms that we see in the head are like propositional atoms, but the atoms that we see in the body may be propositional atoms or these special constructs that are called external atoms. These are higher order constructs that allow us to embed the results of external computations into logical formalisms. So how does it work? So these external atoms are expressions like this. So they take some inputs. They pass these inputs to external computations, for instance, where the feasibility checks are done. And the outputs are returned back into this logical formalism. And this is very much similar to semantic attachments that were introduced in theorem proving in 1970s by Richard Weyrauch, working with John McCarthy. So here is some example. So this is a constraint in this formalism in the ASP, which expresses that it is impossible for a robot R to move from this location to this location if there is no continuous path that connects these two locations. So here, this is an external atom, which basically utilizes a motion planner to check for the existence of a continuous trajectory. And here, as you see, we pass only two locations and check and there is a continuous trajectory between those two. But these external atoms allow us to do further than that, because note that there may be more than one robot. Then we may have to check, for instance, collisions of the motions of these robots. And for that, we can pass the predict name as an input to these external computations. And this is why these external atoms are higher order constructs. They are taking, like they can take object constants, object variables, but they can also take predicate names as arguments. And by this way, we can, kind of experiment with different levels of integration. So we have utilized this framework to implement various robotic domains. And here we see a manipulation domain, and I'm going to represent some experimental results. I'm going to present some results about this domain. So in this domain, there are various feasibility checks. So we have like state constraints, checking whether the robotic arms collide with each other. These are data robots. They are pantographs, so we need to check the collisions between robotic arms. And we need to check whether the payload collides with the environment, with the obstacles. And moreover, we can check whether the two robots that are picking and placing these payloads collide with each other while moving the payload. And here you see that in these two external atoms, we pass the positions of the robots and their orientation, and here we pass the positions of the payloads. But for this external atom, we pass the position of all the robots, the position of all payloads, whether the robots are holding the payload or not, and also the moves of the robot. So here, this requires more feasibility checks. And if you consider like motion planning with multiple robots moving around, then you will also see that the degree of computation increases because the configuration space gets more complicated. And then the feasibility checks take more time, for instance, with such an external atom. So there is some sort of trade-off. Feasibility checks are time-consuming. So how much of integration is useful? So we identified several methods of integration, and according to these three approaches, so we can either perform feasibility checks in advance and then embed them in task planning, or we can compute a plan and then check whether it's feasible. If it is not, then we can do replanning. So these are what we see in many researchers. And moreover, we can embed these feasibility checks into task planning so that they are performed as needed. And this is done by external atoms. So each approach has its own advantages and disadvantages. So these two, for instance, approaches are applicable with many planners or task solvers, reasoners. But this one requires, for instance, these special constructs called external atoms or semantic attachments. So we can combine these different methods in a robotic domain because there are usually many feasibility checks. Some feasibility checks can be performed in advance, some interleaved, and some of them can be checked afterwards. So we provide a general framework to combine all these sorts of feasibility checks. So, which method of integration and how much of integration is useful? So we analyzed this question considering these two criteria. So we looked at the solution quality in terms of the number of feasible plans, and we also checked the computation time. So here are some results for the manipulation domain. Here we use the ASP solver DL8X. So actually this is the only ASP solver that kind of supports all sorts of integration and this higher construct of external atoms. So we use two KUKA U-boats, and we use bidirectional RRT from MOVIT, and also SCI library for collision checks. And according to the results, so if you look at the solution quality, then we see that there are about 2,000 plans that are infeasible and they are computed until we reach the first feasible plan. And with the interlead approach, of course, the first plan that we compute is already feasible. So the interlead approach is preferred more than the other approaches. But then we also see that when we do replanning, it is good to give some guidance. And guidance here is understood is like as additional constraints. Like for instance, if a plan fails, then we try to understand the cause of the failure and then add further constraints to make sure that we get a better plan next time. So in terms of efficiency, we also get similar results. So we see that the interleaved approach computes the first feasible plan in a more reasonable amount of time. So I will conclude with a summary. So after all these experimental evaluations with the robotic manipulation domain, with housekeeping domain, with weighted locomotion, so we have experimented with more domains. All of them are explained in our journal article, and all the ASP codes and representation, they are also included in the journal article. And as a result of these experiments, we have noticed that the full interleaved reasoning is the most promising one, but it is not supported by all the solvers or planners. And so then what can we do? We can apply pre-computation if possible. So if the number of feasibility checks is finite, for instance, then we can apply it. So it is a good idea. But if both of them are not possible, then we have to do replanning, as we do. But some guidance, if we can add some guidance in terms of some constraints, then it is also a good idea. So, thank you.
Any questions? I have one question, let's say it's more a curiosity maybe. You are exploring such logic approach using ASP. I wonder whether, which is your feeling about considering, for instance, because I know of other work including motion or maybe moving robots and logic approach. Let's say considering more complex logics for, let's say, deploying some more, address some more complex scenarios. So, for instance,
Like what?
Like, for instance, introducing time, to consider time in.
I mean, what
task.
kind of, you mentioned more complex logic, so what
No,
kind
no,
of
more,
logic?
no, more complex logic,
okay.
sorry. More complex scenario, addressing more complex scenario with different logics, sorry. For instance, including temporal logics for addressing also temporal issues in controlling robots.
Yes.
So,
so this is not to prove, the idea of this work is not to promote ASP. So ASP just provides a formal framework to be able to analyze different sorts of integration. But in our research, we have, we have applied ASP in various robotic domains, and in some of the domains, we have also considered temporal constraints. And these temporal constraints are basically, they take into account, for instance, the estimate of the duration of an action with respect to their execution in the real world. So we utilize, like for instance, motion planers to get an estimate of, how quick or late, the robot will reach location. So ASP supports such constraints that are based on duration. And I mean, for our in these studies, we have seen that it performs quite well, thanks to external atoms.
Thanks. So I find interesting the fact that in many problems that I've seen, at least, deciding whether are you really in a rush? You have to catch a plane, I guess.
Yes.
Okay.
But it's okay. I'm just going to rush to the airport.
Okay. If you're really, let's say in some problems it's clearly the case that you need to do integrated reasoning. In other problems it's clearly the case that you can pre-compute, and in others that you can, post-adapt. What would be interesting is to find a way to figure out automatically when that is the case and use the appropriate strategies. What are your thoughts on that?
So actually it is, most of the time this is clear at the representation level, because for instance when we want to check the visibility of multiple robots moving in a dynamic environment, then as you may remember, then this external atom gets a bit more complicated, right? So the number of visibility checks required in that case is infinite. So for instance, that can't be done just using pre-computation. So some checks are easy to detect at the representation level. And with a generic framework that allows us to combine these different sorts of methods, then depending on the robotic domain, you can say that this visibility checks should be done using pre-computation. But most of the time it is clear from the representation, at the representation stage.
To a human. To a human.
Yeah, but these are representation-based integrations that we are investigating.
Yeah.
So.
I get it. Thank you.
Thanks again, speaker. The last talk is a paper from the robotics track. It's presented by Luca Iocchi, a practical framework for robust decision theoretic planning and execution for service robots, and this is a joint work with Jean-Pierre. Jean-Pierre is the surname, actually. Okay, so Jean-Pierre, Lazaro, and Wadid. Thanks.
So thank you very much. So this work is maybe slightly different from other works that we have seen in robotics, because we want to focus on a specific class of robots that are service robots, and so we want to analyze what are the features that are needed by a planning and execution systems when it is applied to a service robot. And first of all, I want to share with you some my concern about why planning is not so used in service robotics, and I have analyzed some features that I believe should be addressed more in this domain. First of all, my experience is that using a planning formalism is not so easy for robotics and for service robots, because very often the matching between the robot abilities and the description of the environment is not so easy to be done with respect to the property of the formalism. So my experience is usually it takes a master thesis of a student to maybe fully understand a planning language and the planning system, and to be really able to use it for a problem, especially in service robotics. And the second problem is that at the end, the plans that are generated by some systems are not directly usable in robotics domain. Most of the problem comes from the fact that the assumption that the system will be able to understand a failure and replan is even too strong for robotics. Very often the robot doesn't know that the plan is about to fail, so the robot is keeping on doing the wrong action until a user presses the emergency button. So these two problems, when we analyze the use of these systems for service robotics, we have an initial point, is that in service robotics, the difficulty of the system is not in the length of the plan. So it's not like, I don't know, grid world or block worlds or logistics in which we have to create a complex sequence of actions to reach the goal. Very often the problem that we want to address in service robotics is not exponential in the in the size of the domain, and so most of people prefer to write plans manually rather than write the planning domain, because it's much easier to write the plan than the planning domain. But I think that not using planning is really limiting the development of service robotics, because the complexity that you can achieve with manual plan writing is of course very, very limited. So I think that using planning would be very, very beneficial. So this is very broad analysis. What I've done a little bit of more systematic analysis, taking into consideration RoboCup at home, which is the largest effort in service robotics since 10 years now. And so what I've done during my flight to here, I analyzed the team description papers of the teams that will participate to the RoboCup 2016 in 2 weeks from now. And looking at this, I wanted to see how many of the teams were using planning techniques or similar. So out of 24 teams, only 2 teams are declaring to use planning techniques, one based on ASP and another one on MDP. Then we have 9 teams that are using some ways of writing plans with some high-level tool. For example, the SMAC system, that is a way of writing state machines, or some other tool for high-level planning. And majority of the teams do not even think of this problem, so they don't write anything at all in their paper, and my guess is that they write just C++ code to solve very complex problems. So I think this should be reverted, that we should have best teams to use planning techniques. So Atom robots are complex systems that integrates computer vision, robotics, HRI, and a lot of components. And there is a real need to put together these components in a nice way, in a principled way, but this is not the case so far. So very quickly, some general overview of what has been done for planning in service robotics, and we have some characteristics of the let's say, the planning systems. Classical planning is very efficient, but it requires complete knowledge that is not available in service robotics. Humanoid planning is very interesting because there is an explicit representation of the humans in these planning systems, but there's still some problems because usually they assume that the user is fully collaborative and that the user knows exactly what is the plan and it is under execution. Handy representations are nice because you can model uncertainty and non-deterministic actions, but sometimes they are not scalable, complex domain. And contingent planning is also very promising because there is an explicit representation and sensitive knowledge that is still not too well developed, I would say. So in this paper, we will focus on representation based on Markov decision processes, but we are also exploring some other formalisms. So first of all, we consider service robots. So this talk is about service robots. I'm sure that there are other very nice planners that works in other robotics contexts. But in service robots, the main feature is that the robot is doing services for humans. And this means that the robot has to interact with humans. The robot cannot assume that it has complete knowledge about the environment, and of course the humans are much more unpredictable than the environment. So what are the difficulties when you have a robot embedded in a public environment interacting with users that are not experts? First of all, of course, there is uncertainty in the estimation of the current situation, and if the robot evaluates wrongly its state, it will execute the wrong action. And but one of the most important things is that service robots is assuming to interact with non-expert users. Non-expert users are not aware of the plan that is under execution, and this means that many unexpected behaviors of user will happen. So children will try to climb on the robot or will move the sensors, and this is something that is not considered at any of this level, but it happens when you have these situations. So here you see an example of environment to which we deployed our system. So our approach is based on Markov decision processes, and we have tried to attenuate some of the problems that you have when you use MVPs. One is that the plain definition of an MVP requires an enumeration of the states, but this can be solved by using compact representations. The full observability is also a problem because robots have noisy sensors, and evaluating the current state is very difficult. And we have done an effort to minimize the effect of perception errors by adding explicit observations only when needed. And for the scalability of the solvers, some of them are not very scalable with the size of the input model, and we are using some variables only at execution time in order to not increase the complexity of the planning. So our system has an input, a specification of the planning domain, or the domain that you want to run on the robot. And this is also integrated with another level of knowledge representation reasoning. And it creates a representation of the plan using Petri-net plans, which is a very rich formalism for representing execution plans. And then this plan is executed on the robot. So here, these three components have been, so PRU has been extended from a previous work. PNP was already used as an execution mechanism. And these execution rules are declarative rules that are used at execution time. So the system is composed by an MDP solver. So this is just a compact representation of an MDP. This is an MDP solver that generates a policy. Then we have this layer that is the main contribution of the paper. It is a generator of a Petri-net plan, starting from the policy and from the execution rules. And then the PNP is executed on the robot through the PNP ROS bridge. ROS is the robot operating system. So here in this picture you see two plans. This is the plan that is generated by the planner, and this is the plan that is generated after the PNP generator part. So in this way we are introducing a new level between planning and execution. It is a level that you can call it as plan refinement. This level has the goal of improving the robustness of plans. So this plan may work, but only if everything that is in the model will be actually valid during the execution. The probability that this plan fails is very high, because here there are a lot of things that are not modeled at this level. While this other plan is more robust. It can still fail, because of course you cannot never consider all the possible failure conditions. But this plan is more robust, because it has some way of recovering from possible execution errors. So what are the features of these systems? Okay, here we have the compact representation of the MDP. Here we have a mechanism for explicit observations, so we do as less sensing as possible in order to avoid the impact of sensor noise in the decision of the robot. And these execution variables are interesting because they are separated by the variables that are used at planning time. So I can increase the complexity of the final plan without affecting the complexity of this plan. So this execution variable does not increase the difficulty of planning at this time. So to give you an idea, the generation of the PNP has an input, a policy, and the feature of this policy is that it's not just a state action function, but it contains also the minimal set of observations that are needed to distinguish the non-deterministic outcomes of an action. For example, if an action is deterministic, then there is only one outcome. No sensing is done at all before executing the next action. If an action is non-deterministic, then here we specify the minimal sensing that is needed in order to distinguish which is the outcome of the non-deterministic action. So in this way, we minimize the sensing, but still having the policy valid, so the correctness of the policy is still valid. And with the execution rules, we minimize planning. So execution rules are needed to introduce local recovery procedures so that some problems that appear only at execution time will be solved at this level without affecting the planning domain. So, okay, this computation complexity you will find details on the paper. Here we apply this method in different domains, so with different robots and in different scenarios. And in the last demo that has been done a couple of weeks ago, we noticed that we'll be able to prepare a demo for a new scenario in about 1 week. This, of course, is done by people that are developed the system, but I think that this is a very nice property for a system to give the possibility to prepare a demo in a limited time, a working demo, of course. So let me show you an example. This is a robot office assistant in which the robot is in a corridor of our department, and it detects people at a printer, and after a while the robot goes to the person at the printer and asks to the person if some assistance is needed, and the person can say no, or can ask the robot to bring a document to a person in another office, or to call a technician because the printer has some problem. And then according to this, the robot can do some operations about this. Now, this plan is very simple. It's the policy that is generated from this is very easy. But if you try to run this plan, you will encounter a lot of many situations in which the robot will fail. So, and this is done also at runtime. We added execution rules in order to provide for local requirement. For example, I will show you in the video later that this rule that say that if the person is close to the robot and the robot is close to the target during the go-to action, then the robot has to skip its action. Or, I don't know, if the battery is low during a go-to action, then the robot can go to the recharge station, recharge, and fail the plan. So these recovery procedures state what is the recovery behavior for a robot when something happens during some action. And here, this is, at this moment, it's just a sequence of actions, but here you can have another PNP, or you can have another planning problem to recover the situation. And then at the end, there is the last statement of this recovery procedure that is indicates to the robot how to continue the plan if it's possible. So in some cases it is not possible. So the failed plan instruction is equivalent to the standard replanning mechanism that we have. But sometimes the plan can be continued. For example, you need just to restart an action, or to skip an action, or to restart the plan. In these cases, these situations are considered directly in the PNP without the need of replanning. And we see that replanning can take many seconds or minutes. So this is the PNP that is generated by the system with 17 actions, 45 places, and so on. This is still doable manually, but it starts becoming very, very difficult. And moreover, of course, this is not scalable. If I have this PNP and I want to modify this, it is very difficult, and the probability that I will make mistakes is very high. While this representation is easy to modify. So, for example, if this plan fails during the execution, I can add an execution rule to try to repair this plan. So I will show you how it works this on the robot, hopefully. So here we see the robot approaching, you will see the robot approaching the person. And now this very simple plan, go to the printer and then start interaction. The problem that you see here is that the robot wants to arrive in this particular location. And since since the action go-to is still under execution, the user cannot start the interaction. So one of my students told me, well, we have to change the parameters of the move-based behavior. But this is not correct, because you are just moving the problem somewhere else. So here, with execution rules, say, okay, when there is a person and you are close to the target, then skip the action. Skip action means that the next action of the plan is executed correctly. This is another situation that the robot goes there, now it should start interaction, but there is no person anymore. Guess what happened without the execution rule? The robot will stay there forever, waiting for a reply from the user. While this is not the case here, because the execution rules say that if there is not a person anymore, you have to restart the plan. So we have applied this also in the coaches project. Sorry, this is the noise of the video. The coaches project, in which we deploy these robots in a shopping mall, and these plans have been executed in the real environment. They are still simple, but I think that now we have the formalism to increase the complexity of this task over and over. Okay, just to conclude, please feel free to download our software and to try it. I think that it will be also nice to evaluate if the software can be extended to other languages and to other planners. So the planners are just plugin modules that can be changed. And for future work, of course, we'll continue to do tests and increase the complexity.